All right, now that I think I see enough people are trickling in, let's go ahead and get started. So, welcome to today's webinar. Our new study is available for download. We should have the link in the chat in a moment. It's really nice to see how many people showed up for this. Thanks for taking the time out of your day and joining us for the webinar. My name is Nick Pavlenko. I'm the director of ICCT's Fuels and Aviation programs. And so to kick things off, now that the EU has an ambitious SAF mandate in place, it's time to turn our attention to making sure that SAF actually reaches the market. So given investment barriers and high costs, there's a lot of work still to be done on the supply side to narrow those cost gaps and provide investment certainty for SAF producers. So while we've seen some progress at the EU level with last year's STIP, today's webinar is going to focus on what member states can do to narrow the cost gap for SAF. So before we really get started, two housekeeping items. First, this webinar is being recorded, so we'll send the recording out to all the participants in the next few days. And then second, everyone has their microphones on mute. So if you have questions, feel free to drop them in the Q&A on the control panel. So after the presentation and the panelists' remarks, it's going to last about 30 minutes. We'll spend the rest of the time answering questions from the audience. So today's discussion focuses on the cost impact of different policy interventions that member states can implement to help make SAF more price competitive with conventional jet fuel in the EU. So ICCT researcher Gonja Scheber will walk us through a new techno-economic analysis that evaluates these policy options in detail. And before turning to her presentation, I'd also like to invite my colleague Chelsea Baldino, the fuel program lead at ICCT, and our lead on EU fuels policy to offer a few opening remarks and some context on why this analysis matters, where it fits in. Chelsea, the floor is yours.
Thanks a lot, Nick, for that great introduction. Yeah, really glad to see such great attendance here today. It's been a while since we've done an EU fuels webinar, so great to see so many participants. Ganja, could you please move over to the background slide? Right, so this is our overview. I'm going to provide some background, and then as Nick mentioned, I'll pass it over to Ganja to go over in detail her analysis and our policy considerations at the end, and then we'll conclude with the Q&A. So for some background, Nick provided a little bit of context, but as many of you probably are aware, most sustainable aviation fuel, SAF for short, produced in the EU today is hydroprocessed esters and fatty acids, HEFA for short. So that's illustrated in this map that we borrowed here on the left. Most of those green circles are HEFA fuels, the vast majority. And while HEFA can be really low greenhouse gas, particularly if it's produced from waste oils and fats, in the EU, it's going to be limited. It's when we're talking about the Refuel EU SAF targets, especially as they become more ambitious, even as soon as 2035, we're really going to see a strain on the resources needed to produce low greenhouse gas HEFA fuels and meet those targets. So for deep decarbonization of the aviation sector, the EU will require what we call advanced low greenhouse gas SAF. And that can be broadly categorized into a biofuel category called cellulosic waste and residues, cellulosic SAF produced from waste and residues. Those are identified in the Renewable Energy Directive's Annex 9, Part A, as well as synthetic aviation fuels, which probably some of you at least know are a sub-target of the Refuel EU aviation targets. Those are also known as power to liquids and include renewable fuels of non-biological origin, also as defined in the Renewable Energy Directive. So that's what Ganja's analysis will be focusing on, is what member states can do to support these two kinds of SAF. Next slide, please. So some additional background, some of you may have seen that we had last summer a big report launch where we interviewed, I believe it was 10 industry officials from the advanced SAF industry. And we wanted to figure out what barriers is the industry facing? Why have facilities not reached final investment decision? Why have they not come online? And we focused in 3 different regions, but including the EU, and we found that there's 2 general categories of barriers. The first, on the left, we grouped into what we called the runway. So this is barriers related to revenue certainty. The producers need to show their investors that they're going to have a certain price for their SAF in the future, and that's what gives the investors certainty and allows them to reach final investment decision. This is what is lacking right now in the EU. The STIP was a good first measure, and we hope to see some great initiatives come out of that. And that's what we'll be focusing on today. The side that the EU already has is the takeoff side. So this is the long-term SAF mandate that is Refuel EU. So with that, I will. Oh, and one more point is before Ganja dives in, we focused in her analysis on the Netherlands as a case study. We needed to pick a member state because she had specific assumptions that went into her techno-economic assessment about, for example, grid connection fees or the value of the Renewable Energy Directive implementation credits, specific things to a member state. And so we chose to use the Netherlands for that as a case study, but we know that our results are relevant to any member state. So we hope that there's many different representatives from member states on the call who can benefit from that. So with that, I will pass it over to Ganja.
Hey, hi everyone. Today I'll talk about our results from the recent work. As Chelsea mentioned, we use Netherlands as a case study to understand the impact of policy levers in the EU and how they could reduce the cost gap between advanced SAF and fossil kerosene. I'd like to start by introducing the policy levers that we looked into for our study. You can also find more detailed information on these in our paper. We can broadly classify these policy levers into three groups, although there may be overlaps. On the green, we have the mandates and regulatory support. The blue or the teal is the direct funding and subsidies that are available. And on the gray, we have the market-based measures. And the red framing indicates the national policy levers. For this case, it's the Netherlands, the policy levers that we found in the Netherlands. Within the green, we already mentioned, Chancellor already mentioned the Refuel EU. I want to also point out that in the Netherlands, there's the Dutch Aviation Policy Memorandum that sets aspirational goals and to reduce emissions from aviation in the Netherlands. And then we also have more like regulatory support items there, the Net Zero Industry Act and the Clean Industrial Deal State Aid Framework, which I'd call CSAF, and explain further later on. So these will help simplify the regulatory framework and then would help SAF facilities to come online in an easier way, as well as other clean technologies. So I'll talk more about the financial levers, so the blue and the gray. Like I said, for further reference, you can refer to our paper for more information. So continuing with the direct grants and subsidies, I'll start with the EU-wide options first. So starting with the Innovation Fund, where this is backed by the emissions trading system allowances. It's one of the biggest funding sources in the EU. It's not SAF specific, so SAF projects would need to compete with our other clean technologies for funding. If regular grants or the direct grants could provide 60% of capital and operational costs for a project, and also 40% of these funds could be received before project implementation. Next, we have the hydrogen bank auction. This is more targeted. It offers a fixed premium for up to 10 years for the renewable hydrogen projects upon certification, so verification of the production. This is relevant for SAF because for advanced SAF because e-fuels are produced from renewable hydrogen, so it can act as an upstream subsidy. But the bids from the second auction was between like 20 and 60 cents, although there was a maritime specific bid which yielded higher results. And the third auction just closed, so we'll see what the results from that auction would be. And then finally, the national grants and subsidies. These are bound by state aid rules, which I'll explain in the next slide. But the Dutch government have several programs to support renewable fuels. Nothing specific to SAF so far. There is a support that there are funds for demo and pilot projects, and these could be used for renewable hydrogen and gasification type biofuel production. These are first come, first served. And then there was the awards are around maximum of 30 million. So last year there was a consultation for pathway specific for funding pathway specific to SAF, like power to liquids and alcohol to jet, but nothing materialized from that yet. So nothing specific to SAF yet in the Netherlands. And switching to state aid rules, these regulate how the member state can provide financial assistance to companies or specific sectors, and that these are meant to prevent distorted competition. But the revised rules, which I'll call CSAF, like I said, would help simplify the rollout of renewable energy and would help, biofuels and renewable fuels production to make financial support for these easier. So these could be provided by the member states or prepared by member states, either as an investment aid or a direct price support. As you can see, the amount of aid could go up to 100% of the investment costs. So that's a good opportunity for the member states. And another good thing is that the aid that's received under CSAF, the same project could also get aid from EU funds or other state aids. For example, a project who got innovation fund could also be supported by member states' state aid. And then the market-based measures. The first one is the emission trading system. This requires companies in regulated industries to buy or trade allowances to match their verified emissions annually. And then the free allowances for aviation are phased out in 2026, as most of you might know. So basically, using the projected ETS prices and number of auctioned allowances, we estimated the auction revenues from the aviation allowances, so EU AA. So this is around 0.7 billion cumulatively between 2025 and 2030 for the Netherlands, and 14 billion EU-wide. While these ETS revenues are distributed to the EU member states, we don't know what they are used for, especially for the Netherlands. It could be used to support advanced SAF, and STIP also encourages that. But some part of this revenue would also be used or set aside for the ETS reinvestment mechanism, which I'll explain in a minute. So given these factors, we did not include these revenues as a funding source, but they can be a funding source. And coming to the reinvestment mechanism, which also would call like fuels eligible for the ETS reinvestment mechanism, this is the 20 million free allowances that's reserved for aircraft operators to help offset the high price of SAF. And so depending on the type of SAF that's used, the percent coverage changes. For example, for HEFA fuels, it's 50%. And for e-fuels, for example, it's 95%. But given that e-kerosene or other advanced SAF is not or will more likely be commercially available beyond 2030 or starting from 2030, these funds would most likely be depleted by HEFA fuels before 2030, according to our estimates and other estimates out there. So we did not also consider this. So this reinvestment mechanism would need to be extended beyond 2030. And maybe some part of it should be earmarked or could be earmarked for advanced SAF for them to help with the price or the cost gap. And switching to Dutch emission reduction units. So these are the national implementation of the Renewable Energy Directive. So it's both market-based and also regulatory. So up until the end of 2025, a market-based mechanism that's based on energy, contribution of energy from renewable fuels or renewable energy was in place, but this was recently transitioned into emission reduction units. So accordingly, fuel suppliers can comply with their annual obligations by blending renewable fuels in fossil fuels or by purchasing these ERE credits from other parties that are producing them or importing these renewable fuels. So these will be generated per kilogram of carbon dioxide emissions that's reduced. Aviation is no longer included. It was opt-in before in the previous system. But we assume the co-products from advanced SAF, such as e-diesel or renewable diesel, could be used to generate EREs. So with that, I'll switch to cost of producing advanced SAF in the Netherlands. So this section details the techno-economic assessment we use to estimate the cost of these fuels, along with the sensitivity analysis. So for that, we use the publicly available Fischer-Tropsch model. This is the basis for both the advanced fuels that we looked into for this work. So we adapted the CEA model to the Netherlands conditions. So we changed the economic parameters, discount rates, loan rates, the operational expenses, all according to the Dutch specific costs. And then the model calculates the minimum selling price that's needed for an investment to achieve a specified rate of return. So then we did the scenario analysis by including the relevant economic incentives within the European and Dutch contexts. So the model estimated the MSP, so minimum selling price of e-kerosene in the Netherlands to be around €4.2 per liter. That would make around €5,600 per ton, with a fixed capital investment of around 1.6 billion. The figure also illustrates the contribution, the cost components to the overall, the contribution of cost components. So we find that renewable electricity is the largest contributor, followed by electrolyzer costs and FT synthesis, which are like 32 and 18% of the cost. We consider the point source carbon for this work, but for our sensitivity, we also analyzed direct air capture. So as you can see on the right, we have the sensitivity, but the main focus here is that we want to use this techno-economic model to understand the impact of policy levers. So I invite you also to check the sensitivity analysis in our paper. So as a second advanced fuel pathway, we assessed the minimum selling price for the Fischer-Tropsch fuels from agricultural residues. For this one, so the minimum selling price that we find is like around €2.1 per liter, which is around €2,800 per ton. And the cost components you can see here are the main contributors are Fischer-Tropsch synthesis and gasification. These are both for the same size of facility, which produces 50 kiloton SAF annually. And then finally, the feedstock costs make up around 20%. And when I say, agricultural residues, it's, for example, cereal straw that was assumed. And then switching to the focus of our work, the scenario analysis, where we estimated the impact of some of the policy levers that I talked about in the beginning. So I'm going to provide the results from the best scenario today due to time constraints, but we also have another scenario for e-kerosene. So we considered the impact of, first of all, the reduced cost of capital, the capital grant of 40% of the investment costs, waived grid fees, emission reduction units, and the avoided ETS penalties since advanced fuels would be zero rated under the ETS. So as you can see, with all these options, the cost gap between e-kerosene and conventional aviation fuel, it decreases by 56%. So the minimum selling price decreases by 50%. And you can also see at the first glance that the upfront capital grants are the most effective option. So for this, we assumed, like I said, 40% of capital grant, which would be which would make around 340 million and providing almost around 20% cost reduction. So this is much more higher than what Innovation Fund provides today. For example, it's around 100 million per project at most. But we just wanted to show, what kind of capital grant would, is necessary to make a meaningful impact, basically. So this is just an example that we are providing here. So for the Netherlands case, we also included grid fee waiver. These are like the grid fees that are for extra high voltage electricity that the large scale electrolyzers use. And these are by the transmission system operator in the Netherlands. And so we included those costs in our baseline scenario. And then since in other neighboring member states, for example, in Germany or France, there are some network charge reductions or exemptions for electrolyzers. So when we consider that weight grid fee, it also makes a good amount of cost reduction. It also causes that. And finally, as explained, e-kerosene cannot produce any EREs because aviation is not opt-in anymore. But e-diesel in this case, which is also an RFNBO, if supplied to road or marine sector would receive, or at least we assume would receive EREs. And because the system just switched and we don't know the price of the EREs, the trading price, we use the conversion factor that's provided by the Dutch government. And finally, we did not include the hydrogen bank auction in this scenario because it would result in a change in the amount of capital support that can be provided due to state aid rules. But that's also included in our paper. And next, for the Fischer-Tropsch fuels from agricultural residues, we consider again here the reduced cost of capital. Again, 40% capital funds upfront, emission reduction units, and the ETS penalty. So starting from the initial minimum selling price of 2.1, we see an overall decrease in cost gap between this fuel and fossil kerosene to be like around almost 90%. So the cost comes down to 80 cents. So it's like around 30% more expensive than the fossil kerosene. And so a large capital again is the most effective measure in this case. It reduces the minimum selling price by 24%. Again, for the Innovation Fund, if we consider that, I guess for advanced biofuels, the amount of support is around 50 million euros for the awardees when we check that. But here it would entail a cost of 226 million. And then, for the EREs, again, we considered that this time renewable diesel would generate EREs. So at this price, basically, or with these cost reductions, FD fuels could be cost competitive also with HEFA fuels. So with these two examples, I think I will switch to some policy considerations. So our scenario analysis could help identify the impact of policy combinations and then the level of support that might be necessary to further narrow the gap. It can also inform the amount of support necessary through a revenue certainty mechanism, for example. We think that. On that note, I want to conclude with some conclusions. So to help the first generation of advanced SAF take off in the near term, so as I try to explain, the member states could take advantage of the relaxed state aid rules. So our analysis shows the level of support that would make a meaningful cost reduction. So it should be in the levels of 300, 400 million euros per project, let's say. However, these high award levels may not be necessary if the producers also have access to revenue certainty mechanisms, for example, which we did not assess in this study. So with its current structure, the emissions trading system will not be able to bridge the cost gap between advanced SAF and fossil kerosene. So I already mentioned that the feeds, the 20 million allowances, would be depleted by the HEFA fuels, but the member states could reserve part of their ETS auction revenues for advanced SAF support, for example. And for the, sorry, I forgot to mention, for the feeds reinvestment mechanism, we looked actually into the amount of allowances that would be necessary to cover the cost gap for 2030, for example. So it will make around 15 million free allowances that would be necessary to cover 95% of the cost gap for e-kerosene using the e-kerosene price from the study. And finally, I guess the aviation-specific hydrogen bank auctions could be organized, which this was announced under the STIP. So it might help increase the auction prices from the hydrogen bank if it is aviation-specific, as we saw that it worked for the marine-specific auction, that there were higher price. And there are also some constraints, like I mentioned, for the use of hydrogen bank auctions with other state aid. So yeah, that's also maybe something to consider for the future. So with that, I'll conclude. So thanks for your attention.